The solution to the least squares problem allows us to tackle what's known as the linear regression problem in statistics. So let's just take a couple minutes to review what the least squares problem is and how we solve it. Let's suppose that A is an m by n matrix and that B is a vector in M space. And let's suppose that AX equals B is inconsistent. So in two-dimensional space, we might have a three-dimensional space, we might have a picture that looks like the following. Let's suppose that we have two vectors, v1 and v2, that are in R3. If I look at the matrix whose columns are v1 and v2, and I multiply it by vector x, whose entries are x1, x2, we've seen before that this is really x1, v1 plus x2, v2. So as x1 and x2 vary, what we do is we generate various linear combinations of the vectors v1 and v2, and provided v1 and v2 are linearly independent, the set of all linear combinations will give us a plane in R3. So AX, that is going to generate all the linear combinations of v1 and v2. This is v1 and this is v2, which will give us the plane. So the column space of A is just the set of all linear combinations of v1 and v2, which I'll denote by capital W. Now, to solve the least squares problem, what we did is we took a situation when B was not in the column space, so we could not write it as a linear combination of v1 and v2. That's why it sticks out of the plane like this. And what we tried to do is we tried to find the particular linear combination of v1 and v2 with the property that if I look at the distance from B to AX, that's a tilde, that distance is as small as it can possibly be. So if I chose x1 and x2 to be something different than x tilde, I might get a point over here, and the distance from this point up to B would be quite a bit larger. So what we're trying to do is we're trying to find the vector that minimizes the difference in length, the length of the difference ax minus b, and it's given by the least squares value x tilde, which is determined using the following formula that we derived before. We take A transpose times A. That matrix has to be invertible if the columns of A are linearly independent. We take the inverse of that, multiply it by A transpose, and then multiply the result by B, and that gives me the particular linear combination of the columns of A to make this distance as small as possible. Let's take a look at the least squares problem, the simple least squares problem in linear regression. So I have a situation here. I've got a bunch of data points, and I'm trying to find the line of best fit. We all have a good sense of what that means intuitively, but we want to take a more mathematical approach right now. So one of my data points is x1, y1, x2, y2, x3, x4, x3, y3, x4, y4, so on and so forth, up to xn, yn. So n is the number of data points. And the equation of the line is what I want to find. So I'm going to write it in the usual y equals mx plus b form. But instead of using m and b, I'm going to use beta naught for the vertical axis intercept and beta 1 for the slope. So we're going to take a look at each of the lengths, distances, from the data point to its corresponding point on the line. Now, the y value of the red dot is y1. The y value of this point on the line would be what I get if I plug x1 into my linear function. Again, we don't know what this linear function is yet, but that's what it would be. So beta naught plus beta 1 x1 minus y1 is actually this distance right here, which in this case would be negative because this point, which is represented by that, is below that point. And I do the same thing at the other points. For example, at this point, the coordinate of the dot, the vertical coordinate, is y4. If I was to plug x4 into the equation of the line, this is what I would get. And again, in this case, the difference is negative because the point is above the line. I would do the same thing over and over again. Points that are below the line would actually yield a difference that is positive, and so on and so forth. Okay, let me just double check that. Y4 Yes. So in this picture, when the dot is above the line, this difference will be negative and vice versa. So what we want to do is we basically want to add up all these errors and try to minimize them. Now, because there could be cancellation between positives and negatives, it's better to actually square the distances. And that's what we do. We compute what statisticians call the sum of squared errors. So here's what it is. We take each of these distances, and we square that distance, and we add all of the results together. So I'm taking all of those distances, squaring them, adding them together, and this should be y sub I right there. That's the sum of squared errors. And we want to find the slope, beta 1, and the intercept, beta 0, that makes this as small as possible. Well, there's a nice way to do it using tools from linear algebra that we've been discussing lately. We're going to introduce some new notation. I'm going to let beta be a vector made up of beta 0 and beta 1. I'm going to let the vector y be a vector made up of our observed y values, 1 up through n. And then I'm going to let capital X be an n by 2 matrix. The first column will consist of 1s, you'll see why in a minute, and the second column will consist of the x values of our data points, x1 up through xn. Let's take a look at the difference, x beta minus y. So here's x, here's beta, and there's y. So I would take the first row and multiply it by that column. I would get 1 beta 0 plus beta 1. That gives me that quantity. And then I subtract y1. Going to the next entry, 1 x2 multiply by the corresponding entries there, I would get beta naught plus beta 1 x2, which I've written here, and then I'd subtract y2. And I do this for each of the data points, and what I have is the following. Now this is a vector that is of size n by 1. If I take the length of that vector, I would take each of these components, square them, and add them together, but that's exactly the norm of x beta minus y. So the sums of squared formulas we saw on the sum of squared errors formula we saw on the previous page is basically this length squared, x beta minus y. Well, you know, if we're trying to make this as small as possible, forget about the square, and let's just make x beta minus y as small as possible in terms of length. So that's the quantity we want to minimize. Now we're looking at a least squares problem. In the least squares problem, we were looking at ax minus b. Now we're looking at x beta minus y. I want you to identify the x in our situation, which has a column of 1s, with the matrix A in the least squares problem. Identify the vector beta that we're trying to determine with the vector x that we were trying to determine in the previous problem, and then the vector y in our problem, identify it with the vector b in the original problem. And using the formula that we had, we can actually, for the solution, we can actually write beta as x transpose x times x, quantity inverse, times x transpose times y. Okay, so let's just check the dimensions of that. X is n by 2. So if I take x transpose, that would be 2 by n. So x transpose would be 2 by n. So this would be 2 by n. This would be n by 1. X transpose times x would be 2 by 2. So if I take the inverse, it would also be 2 by 2. So sorry for the crappy writing, but This is 2 by 2, this is 2 by n, this is n by 1, so the result, the end result is that beta will be 2 by 1, which is exactly what we want. Now in practice, we don't actually use the inverse, but instead we perform a QR decomposition of the matrix X. Then what we do is, so we get R beta equals Q transpose times Y, and we've discussed that in a previous illustration of the least squares method. To solve for X, we then set Z to be Q transpose Y, and we solve R times beta equals Z using simple backward substitution. But in any event, just to summarize, take your matrix X by slapping a column of ones, and then the X values of your known data points. Let Y be the Y values of your known data points. And then the coefficients of your line are then stored in the vector beta, which is determined in this manner. Now this idea extends to multiple linear regression. Multiple linear regression is the idea that your inputs are no longer just scalars, they're actually vectors. So my inputs would be vectors, and for each input vector, I have an output. So I'm going to write x sub I in components as xi1, xi2, up through xim. So each vector xi is in m-dimensional space, and there are n of these vectors, which keeps track of the number of observations, which is n. What we want to do is we want to be able to write y as a function of the variables x1 up through xm. So we're going to have beta naught plus beta 1 x1. Notice how that's just the simple linear regression a couple moments ago, plus beta 2 x2, so on and so forth, plus beta m xm. We want to find the coefficients beta 0 up through beta m so as to minimize this sum right here. This sum is exactly analogous to the sum we saw in simple linear regression. In fact, if you cover up all of this stuff, you get the same formula we had in the linear regression situation. It's just that we now have more variables. So that would be x beta time minus y, the length of that quantity squared. Beta is made up of beta 0 up through beta sub m. Y is made up of y1 up through y sub n. Again, m is the number of input variables for our model, and n is the number of observations we have. So in this situation, x would be, we have a column of ones way over on the left, x11, x12, x1m. Those are the entries of our first observation vector x1. And because these are along a row, I'm going to write that as x1 transpose. Same thing here. These are all the components of x2. So I've got a 1, and then I have an x2 transpose. And then I go merrily along my way. So x would be this. It's going to have size, let's see, what size is it going to have? It's going to have, this is going to be xn transpose. This is going to be, each of these vectors will be m by 1, and then I'll have a 1 here. Xn is m by 1, so its transpose would be 1 by m. Okay, so to summarize, in this situation, this solution would be very similar. X would have n rows, m plus 1 columns. Why m plus 1 columns? Because we have m entries, but then we have this extra 1 over there. Beta is going to have size n plus 1 by 1. Y has size n by 1. So if I take x transpose x, that's going to have dimensions m plus 1 by m plus 1, and so will its inverse. X transpose will have dimensions m plus 1 by n, and y has dimensions n by 1. And if we look at our dimensions then, x transpose x, here are the dimensions of x transpose x, it ends up that beta will be m plus 1 by 1, which is exactly what we want. So the easiest way in the multiple regression situation is to look at your observation vectors. Take the transpose of each of them, lay them across the rows here, augment on the left with a column of ones. Then, to get your n+1 regression coefficients, use this equation. This will involve computing an inverse, and of course the easier way to do this is to use the QR decomposition.